Today, I try to give you an introduction to what we will discuss later on. For some of you, most part of these slides are already known, but for some other one not, so I will try to cover again in this part. And basically, we will discuss during this second part of the course what in large part has not been discussed before. With Professor Yomo Lee, you have been discussing how to make membranes, basically, how to prepare membranes. We will not discuss how to prepare membranes. We will discuss mainly how to use membranes, why it makes sense to prepare a lot of membranes. Keep in mind that in some operation today, running already, single plant installed in desalination or in some wastewater treatment, you can have up to millions of square meters of membrane installed. The plants of the program Megaton, there are 3 million square meters of membranes. So making membranes today is a very important task. These membranes have to be always the same, and they are not easy. They have a film, as you learn, very thin, microns, with very specific structure, level of porosity, size of the pore, has to be always very well controlled. So making membranes is very, very important, and still we have to learn and to improve how to make membranes. But we are making membranes because we want to use them. And the motivation for making a lot of work in membrane preparation is to the very large success that membrane operation have today in many different fields. You will see that I will try to show you that membrane engineering, in principle, is contributing today to the major problem that we are discussing in our society every day in the newspaper or in TV. Water, energy, raw materials, biotech, climate effect, gas separation, CO2, etc. They're all a problem where membrane engineering has a very significant role today and more eventually in the future. Some of you already know about this report, and I'd like to mention again, if you want to know more what can happen in the 2050, we have in Europe a club sponsored by European government, sponsored by the Dutch government. It's called this Skyline Delft Debate. It's a group of professors, basically most part of them chemical engineers professor, and they are discussing how will be the industrial world in the 2050, about 40 years from now. This is one of the first report which has been published. And it's interesting to read because, first of all, if I'm showing this report to you, is that because a lot of membranes are discussed in this report. This report is discussing about everything: transport, energy, health, food, water, any problem which exists. And you will find a lot of reference, a lot of mention of the contribution that membranes can have in the logic of what we call process intensification for the solution and for the redesign of the world, industrial world 2050. It's also interesting to mention that some of you are already familiar what we call Horizon 20. How many of you know what is Horizon 20? Never heard Horizon 20? In Europe, you know, we have 28 countries, 27 countries, and we are working all together. Every 5 years, we elaborate a new strategic big research plan, a program for innovation and research. Sometime we make 5 years, 7 years, depending. The one running now from 2014 is called Horizon 20. It's the largest research plan never designed by the European Union. There's something about 80 billion euros of money involved, a huge amount of money, where for everything, any kind of research program in all the different areas, from nanotechnology to water problem to climate problem, health and the social problem, etc., etc. It's interesting that if you're reading Horizon 20 program on the web, you can find a lot of information. You will find that a lot of the discussion that are present in the research agenda on process intensification, including some called just the third process intensification, are part today of Horizon 20, which means there's been a very good interaction between scientists, academia, university, research center, and technocrats in Brussels, from one side. From the other side means that a lot of these suggestions that this club of professors been offering are now part of the new call for proposal and for the research that from 2014, this year, until I think 2020, I don't remember, I say a little bit more, it's 6 years or 7 years, will be under the umbrella of this logic, and which means a lot of membranes. And that is just because we have to work more and more in this membrane engineering as a part of the process intensification strategy. And this is worldwide, because now Horizon 20 is open to collaboration with any country. Formally, for the first time, for example, if you read the project of the Chinese government, you will find a clear indication, a clear request to the Chinese researcher to work together with European in Horizon 20. Same is true for Korea. Korea and Europe, Korea and China, they signed an agreement, protocol, just for creating partnership between Korean researcher, European researcher, Chinese researcher, European researcher. There's a special money that will be utilized to sponsor joint proposal. That's why there is a lot of this conversation going on. Shortly, because most of you are already aware, because you heard many times, if you want to know more about process intensification strategy, you will find a different, if you go on the web, you will find different reference today. There are conference, books, classes, course in process intensification. 5 years ago, 7 years ago, this term was unknown. If you were going on the web, nothing. Today, a lot, maybe too much. Basically, process intensification strategy means that we have to redesign completely most part of the basic unit operation of process engineering. All the way of doing that means from distillation to crystallization to emulsification to condensation to sedimentation, all the different basic unit operation that engineers has to use to realign their process has to be carefully analyzed and carefully eventually redesigned for avoiding the trouble and the problem that we have been creating in the past years, when a lot of things were possible in the past because boundary conditions were different, not possible today. Footprint, this size of the plant has to be much, much smaller than the one we are using in the past because there is no space anymore. So we have to try to reduce footprint. We have to try to reduce contamination, environmental problem. In the past, people were not taking too much care because we had a lot of space, the amount of production were much lower, so it was less severe problem. Today, no way. We must be very careful to avoid any environmental impact or significant environmental impact, etc., etc. So what we have to do is to have new unit operation with consuming less energy and consuming less raw materials, because the amount of material is all the same. Population is increasing, industry is growing, and raw materials are disappearing. As some of you remember that when people today are talking about water stress is problem number one, but the other problem, much less, well, no, people are not talking too much, is that the raw materials are disappearing. Some part of the world we have been losing from 75% to 80%. We have depletion of the material that people were extracting from in the mines, etc., because we have been not taking control, discharging the wrong way, etc., and a lot of metals are disappearing, and the industry is requiring more and more. So we need to consume less energy and to take care of the raw materials. We have to try to decrease cost, more security. That is one time people were not aware, today we are. And we have to, this new system is changing very quickly. Now everything, one time a new technology will stay on the market for 20, 30 years. Today, every 1 or 2, 3 years, things are changing. And that's something that is, we have to take care in production, etc. For doing this, we have to increase efficiency, a small footprint I was mentioning before. We have to control all the kind of emission, gas and liquid. Automatization, remote control, etc., is part of our life more and more. And in the past, these things was not a problem, was not existing. So sometimes we have to redesign, taking care of all of these aspects. Not easy, because this is not just talking and making a smaller footprint, etc. It's much more than this. If you want to realize this kind of objective, there are principles and objectives that you have to take care. And they are very sophisticated. Basically, what we are talking, that we are moving from one kind of industrial development where quantity and was the most required final goal, to produce a lot, etc., to a new kind of society, new kind of production where quality, that means the contribution of human capital of understanding the problem is much more significant than in the past for obtaining the result. And you see here, for example, we have to maximize the effectiveness of intra and intermolecular events. So we have to understand at molecular level what is happening when we make a chemical reaction. Engineers in the past were not aware, eventually chemists are not engineering. Today, engineers have to be very aware of what is happening here to avoid the problem in production of chemicals that can kill or can induce disease and that we unexpected and so on. So this is very important aspect at molecular level. We have to try to give the same level of same efficiency at molecular level to each molecule that we are using, to avoid the problem of hotspots or deviation from the final result, etc. And that means, for example, that we have to focalize on space uniformity, the process to be the same at any level. So we want to avoid, for example, thermal temperature gradient, concentration gradient, or pressure gradient in different process, etc. Not easy, but has to be done. And more engineers, not just chemists and physicists, are learning about this. We have to optimize all the driving force that we are using in our system for separation, for chemical reaction, etc., at every scale, and maximize the specific surface area to which this kind of forces are applied. A big control of what is really happening. By the way, when you are talking about maximizing driving force and basically on the specific, maximizing specific area, this means to control all the transport across the interface. Best configuration, in best way to realize this is to have membranes. Membranes are just interface. So if you can control mass transfer, energy transfer across membrane, you satisfy these kinds of requirements, etc. we have to try to maximize synergic effect from single partial process. At the end, we have to realize one single system in which all the processes are very well integrated. Not easy. One of the interesting aspects of a membrane system that we maximize this. Remember that in membrane engineering is not new. It's reproducing most part of the phenomena which take place in nature in our body. And in our body, our biological membranes, they have tens, sometimes hundreds of different functionalities working together in single membranes. Today, engineers are far away to reproduce what happens in biological membranes, but we are working on the same line. And already now we try to integrate 2, 3, 4 functions. You have a separation and chemical reaction, and we will discuss in membrane reactors. In nature, you have everything. You have a separation, chemical reaction, different kind of separation, different kind of chemical reaction, energy transfer, information transfer, etc. in a single membranes. We are not able to do this, but that is the logic, and combining function, again, in membrane engineering is one of the goals in which we are trying to do something similar to what happens in nature. So these are just some principles and some objectives of process intensification, just to mention that it's not easy to realize this goal, because it means very dramatic change in the understanding at molecular level phenomena that in the past were not important, particularly at the industrial level. Professor, researcher have been always interested in some of those, but not engineers. Today, engineers are working with the researcher to make these things real and very well understood. And combining function, transport, control of mass energy transfer across the interface, space uniformity of all the kind of gradients, and control of orientation and energy molecular collision are just the aspect that we have to control with attention. For doing this and to reach some results, what is happening is that we are redesigning, I was mentioning before, most part of the unit operation. In some cases, just upgrading, improving. In some other cases, it's dramatic change. Again, here we have to redesign all these separation units. Molecular separation units today are very, very significant. Keep in mind that in any industrial process, in the running cost, not capital, but also the capital investment, but for sure in the running and the operation cost, separation sometimes covers 80% of the cost. The cost of the chemical transformation, etc., is marginal compared to the fact that at the end you have to separate different components. And the cost of the separations is in medical production, in biotechnology, but also in some other more simple areas as textile or leather, it can arrive to 80%. And today we have to control this cost for molecular separation. Reverse osmosis, that we have been discussing already, ultrafiltration, nanofiltration, electrodialysis are all the units that are useful for realizing this request, which is part of the process intensification. And we have to have a new catalyst design and chemical reactors, because we want to control the effectiveness of every single unit, etc. How can be done? Membrane reactors, that we will try to discuss during this class, is one of the ways to redesign most part of the chemical reactors. Instead of having only stirring or CSTR or fluidized bed, etc., we will talk about MBR, we will talk about bioreactors, membrane reactors, etc., because they can just give some opportunity, including what is called a catalyst design. That means we have a lot of catalysts, quite interesting, but they are not appropriate, not easy to use in real life for different reasons. Too expensive, poisoning, a very short lifetime, etc., etc. Enzyme is typical. Enzymes are biocatalysts, but they have very short lifetime. For increasing lifetime, we have, for example, to make immobilization. If you immobilize the protein, the few hours, few minutes of activity can become months or years sometimes. Membranes is not one of the ways to reach these objectives, to have catalytic membranes where with enzymes are immobilized in the membrane phase. And we will discuss about this. In some cases, we also have to introduce new kind of unit operation to satisfy process intensification for mass and energy transfer between different phases. And as some of you already heard about membrane distillation, membrane emulsifier, etc. We will mention a little bit again, but that is another part of the story. Membrane engineering is doing all these things. In all this line, for redesigning process engineering, we can introduce unit that familiar to you, the one who attended the first part of the class in the spring. They know about the reverse osmosis, nanofiltration, etc., pervaporation, and so on. You will know in this class about catalysts. Some of you already know about membrane distillation and membrane crystallizer, etc. It's interesting that if you do this kind of activity, there will be significant impact on some of the most important problems we have today. Energy, as you know, is quite interesting for everybody. And energy means electricity, and that means fuel cell, salinity gradient, battery, are all problems related to membrane operation. Water and mineral resource is nothing more than big development in desalination with membranes, in recovery of minerals through some specific membrane operation. And all the industrial production can be rationalized for having the benefits we are talking before using membrane operation. Basically, we discussed already, and we will try to discuss again, to show that the membrane technology can go from trying to cover all the problems we have been discussing before, minimizing also some of the trouble that were present in the other system, and as I was mentioning here, molecular separation, chemical conversion, etc. And this industrially will be water. Keep in mind that membrane operation today are a dominant technology in water treatment. Years ago, when I was a student as you, the impact of membrane operation in the water area was 4%, 3% in the 1670. If you see the plot, well, today is 80%. Big transformation. Not in any problem, in gas separation, not at this level, in some other area not, but in water for sure, and also in some other one. For example, in food. Food people not talking too much, but in food industry, a lot of membrane operation already present. Public is not ready to understand, and food is a little bit sensitive area. People can be afraid if you tell we are using polymer, your competitor will tell polymer can release something and you can have disease, etc. So there is no big information. But every time you drink a wine, for example, or you drink a lot of beverage from a beer to orange juice, etc., a lot of membrane operation are involved in the industrial production. All the beer, good beer that you are drinking today, the water for the preparation of beer is going through purification with membranes. All the wine that you are drinking in the production line, there are 2 or 3 different membrane operation. The standard one is before bottling. Before bottling, you have this last purification from microorganisms, etc., is done by standard, by microfiltration. But today, you have also a lot of process. Reverse osmosis is used to increase the sugar content, for example, before fermentation. If the sugar content, if it's raining during the harvesting, as this year, so you have to increase a little bit the sugar content, they use RO. But it's not visible, it's not big talking about this, but a lot of membranes are there. And more and more in petrochemical industry, pharmaceutical production, etc., the principles of membrane engineering are becoming quite significant. This system are already present at the industrial level, as I was mentioning, and they are all quite consistent with the principle of process intensification system. So that is what is our goal in terms of footprint, in terms of efficiency, and in terms of more optimization in consumption of raw materials, recovery and reuse, environmental effect, etc., etc. Remote control, all the membrane operation can be very easily automatic. And there's no way you make an MSF, etc., total automatic. Keep in mind, if you want to make membrane distillation or any other membrane units, RO, etc., there are plants I was always mentioning because I saw by myself. If you go in Egypt, 80 kilometers in the desert south of Cairo city, you have a big ultrafiltration and RO plants, but the engineers controlling this plant are not sitting in Cairo. They are sitting in London or in New York or in Milano. And from there, they can easily, when the signal arrives, they can easily control what is happening. No way to do the same with any other technology, and can be done with membrane. So this last part is becoming more and more important, because it does not mean only the desert. It means, for example, the space. When you hear about space lab, etc., a lot of membrane operations are present in this kind of system, and they would be present in the future. And there is also evidence of some result. This is not only academic approach anymore, because the reason for which reverse osmosis is today a dominant technology, because reverse osmosis is decreasing the cost of desalination, production of water, for a factor of 10, not 10%, factor of 10. And MBR, which is another best available technology in water treatment, water reuse, can give you 5 times decreasing in footprint and volume than traditional system. You have 5 times more compact than any conventional biological treatment, etc. And when you are going to work with membrane reactors, you can have conversion which is 5 times higher than the same reaction carried on in traditional reactor, etc., etc. So there is a lot of evidence that some of the hypotheses and some of the motivation that are suggesting to work more in this area has been already verified in real life, not in the lab, not by professor, but in the real logic, satisfying very well all the logic of process intensification. Much less footprint, much less energy consumption, increasing of efficiency, etc., etc. Some numbers that I was mentioning before, some market trend. This is the situation of today in desalination. This was a few years ago, I think 2013, which means data coming from 2012. And you can see here that already in 2012, basically, RO was covering 60% of the desalination. This number today is 80%. Today means for 2016, next 2 years, this will be 80%. Already now we are about 70%. Keep in mind, it's quite important, and some of you already know the situation, we will see a little later. Today, we have an installed capacity for fresh water production of the order of 65 million cubic meters of fresh water produced per day, with the membrane that Professor Yomoli has been showing you. So very well justified to learn very well and to understand how to make membranes, because this is not a joke anymore. There's a lot of money involved here, because the huge amount for producing this, you have millions and millions of square meters of polymers, polymeric membranes, basically. Huge. Now, I told you single plant, sometime I will show you some, install 3 million of single plant or square meter, 30,000 modules in a single plant. And you can see the competition with MSF and other process is going to be quite severe. MSF, when I was a student, was 95%. Basically, everything was MSF. Today, MSF is becoming a small part of the story and slowly disappearing, basically, and everything is going to be membranes. Not only food, or not only water. If you analyze all the sectors, I was talking to you about food and beverage, where not too much is public. People are not talking. You never see advertisement about the membranes using wine or food. They don't tell you about. But you can see here that how the request for membrane module in food and beverage is growing and growing years by year. Was basically very low in years ago, but today is just the prediction is still big, increasing all around the world, and there will be more than what is now. And that is motivation are quite interesting because they are all consistent with the process intensification logic. Again here, that is the prediction that I was mentioning before, is 80% is 2016. So in next year, next Christmas time, you will have this, the 60 I was showing you before is going to be 80. And this can be a real number because these things don't happen every month. There is already plant under construction that has been designed and we know what is going to happen. So that is the number, and eventually the only thing that can happen instead of 80 can be 90, because countries, China for example, that is not too fast in membrane, that was not too fast. Today I'm just coming, as you know, from China, and all around China they are building center of excellence on membrane engineering. I was showing some of you yesterday the huge new installation that they are designing today for industrial park, totally devoted to membrane production and to membrane research. And that basically is what is going to happen. Just to give you an idea of the plant existing already today, no, these are all plants installed basically last year, the end of last year. And you see that the productivity of the order of 500,000 cubic meter per day. And the cost in any case is of the order of total cost, I don't know if the cost here, but I can tell you the overall cost normally for this plant is similar to the capacity. Millions, no, $500 million or something similar. That's the same number. Consumption of electricity is quite interesting. Overall cost for the water production, 58 cents of a dollar, going still down, or 50, 48 in Singapore, etc. And this was scheduled October 2009 and went in production in 2013. 500,000. I'm showing this because some of you already know this is Sarek. These plants are going to be obsolete already now. They just started operation last year, but this 500,000 is small. People now in Korea or in Japan or in China are already working on plants that are 1 million cubic meter per day, no 500,000. So these plants are becoming old just much faster than expected. And these plants are all the same size. There's another one in Algeria, 500,000, the same third quarter 2013. Cost of production again, basically $500 million, 500 millions roughly. And if you go ahead, having the same. I was mentioning that you don't find this kind of plant in China. China is a very important market, it's clear to everybody because it's the largest market, single market in the world. However, China is changing very, very quickly. China is the only country where just to recovery, the fact that they are not ahead in this area for the moment. By the way, Chinese researcher in the last 3 months, if you go in journal Membrane Science, where Chinese researchers were absent 10 years ago, there was nothing from China. In the last 3 months, there are more publications from Chinese researchers on the journal Membrane Science than from the United States of America. The Chinese have been overcoming the United States of America researcher in journal Membrane Science, which is quite evident what is happening, which is consistent with this story. in China, they are building industrial park totally devoted to membrane engineering, to speed up and to recover the fact that they are a little bit behind. This is one in Nanjing. There are 60,000 square meters of space to install industrial membrane company, research institution, university branch, etc., all in this area, doing everything, not a single process. They do every kind of research activity, and they have just attracting research institution from the industry, from the university, from a specific new agency, etc., for doing, as I was mentioning before, CO2 problem, clean combustion, metallurgy, desalination, water, etc., etc. A very large integrated area. And in Nanjing, where one of your PhD students was here until recently, Zhao Liang, who some of you are familiar with, he is now working in this place, and he already has his lab, etc., etc. He left here. Well, he was working by himself. Now he has 5-7 students working with him. In this place, there is an institute on membrane technology, and the application, the student entering every year. This year I was there when the class started, where 55 new students registered in the Membrane Institute. In total now there are about 220, consider the last 3 years. They started in 2009, I think. This year we're 55 in single institute. And again here you see they are doing basically what I was mentioning before. Each area of interest is just present. Fuel cell, biomass, natural gas, wastewater, water purification, energy, conventional industry, food, pharmacy, metallurgy, petrochemistry, electronics, covering any area, basically. 50 minutes from here you can go swimming or take the boat overnight in Weihai, where I was yesterday. They are building something similar. I show you the picture of some of you, huge skyscraper where there is basically about 15,000 square meters are devoted to create a EU-China membrane center for covering most part of these things, just in front on the other side of the yellow sea that is here. I was mentioning that the motivation and the interest to rationalize, to develop all these things is related to different problems. One of them is clear here, which is not a problem, it's quite positive, is the significant world population that is growing exponentially in the last time. And with this, the fact that we have many more billions of people on Earth than we had before, in the 80s we were less than 2 billions. Now, in the 80s, last couple of hundred years ago, we were 2. In the 2000, we were of the order of 3-4 billions. But you see here in 2050, the one that we are studying as a Skyline debate, we are going to be about 10-12 billions if nothing happens. That means that the land is all the same. We will go into space, but still Earth will not change too much, and the water and the food and the raw materials has to satisfy these numbers, 10-15 billions instead of 2-3 billions. And that can be done in principle if research will be able to do it. So process intensification is a reality, and if we don't do it, there will be a lot of troubles. And when you are talking about this thing will affect overall global warming, is a part of the story. Energy consumption will increase by definition. But, for example, there are problems less familiar to most of you. By depletion of raw materials, people don't know that the percentage of mineral disappearing from soil in the last 100 years, in most parts of the world, is of the order of 70-80%. Minerals are disappearing for a large use, but very bad control. People were not taking care. We were not taking care at home. when we were using copper or manganese, etc., no one was taking care. We were putting the garbage and forget. Now people are starting to realize that if we are not careful, lithium, vanadium, manganese, and magnesium, etc., are disappearing. And we have to find a way. Already fighting all around the world is starting. China is controlling a lot of these minerals. And now they start to have control on the export. And we took China in court at international level because that can affect all the electronic industry, advanced technology all around the world. So that can be origin, not only water will be the origin of fighting, but raw materials. That's why we have to introduce new technology, new way of thinking in the logic of process intensification to avoid this. And so new technologies are becoming important, and we will discuss a little bit, or we discussed it already with some of you. For give you an example, quite important from my point of view, and this is a research, does not exist yet. But in perspective, what has to happen today in desalination, for example, water stress is problem number one. The real problem is always, everybody's talking in desalination about energy consumption, and we have to reduce energy consumption, etc., and brine disposal, because we have a lot of brine. When you produce, as I was mentioning before, 65 millions of cubic meters of fresh water per day, that is a number that you can remember. But there is another number that people don't know, that for these 65 millions of cubic meters of fresh water that everybody likes because we can drink more, we can make irrigation, etc., there are 37 millions of tons of brine produced. Huge mountains, Himalaya of salts that we don't know what to do with. And that's what we call a brine disposal problem. Everybody is working on brine disposal. Our logic, some of you already are familiar, that tomorrow, if a young researcher will do their job in the right way, this problem can be quite interesting, can be totally reversed. Forget about the water. The real problem in the future is much more than water. We have a lot of water. And we have the technology already existing to clean the water and to better distribute. In terms of research, everything is clear. Eventually, it's a question of money, but money is always an artifact. When people are telling you how much costs, etc., forget. Money is always an artifact, not for the people who don't have the money, but money is the less important issue on earth. Money has been invented. Years ago, money was not existing. Money is only a way to simplify the interaction, but it's not the real problem. The real problem is how to solve the problem. And you don't solve the problem with money. You solve the problem with technology, with science, with understanding, etc., etc. So the real problem of tomorrow will be totally different. Instead of energy consumption, desalination will be energy production system with blue energy. We will discuss about pressure retarded osmosis, reverse electrodialysis. There's a lot of energy available on Earth where salty water and fresh water mix together. That is not used, zero today. There's not a single watt coming from blue energy, from the free Gibbs energy of a concentrate solution against a fresh solution, because there are no membranes available. But if you put the membranes when a river enters in the sea, you can produce, as in nature is already done, a lot of energy that can cover more than 25% of the total energy request on Earth, more than the nuclear energy, much easier than wind or solar, basically. So in perspective, tomorrow, this problem will disappear because the desalination will be a way to produce energy. And no brine disposal, because desalination will also produce minerals. You have 65 million cubic meters of fresh water, but you have 37 million tons of salts. If you understand how to integrate the two things and producing something interesting, forget this problem and look to this future. So basically the water price will be free for the people, as public is asking already today. When you talk with the people about water price, already people are, if you go in Middle East or in some other part of the world, people are very nervous We are water, as you know. Most part of you look so solid and big, with a lot of strength. You are water. 70% of your body is water. So if somebody is putting a tax on your body, you will become nervous. Because in water, we want to keep control of the water. Water is our life. We are water. So this logic, if you look the same scenario, but you focalize not water, but around the other part, that means we have desalination, but desalination will be a way to produce energy, PRO and R&D, and to produce high quality raw materials during desalination. And water also, but the water can be sold at production cost with no profit, no making money on water. It's interesting, and some of you are already familiar, that this was an academic approach, and interesting but academic, and professor can talk how much they like, but never happened. It's not true. Because today, around the world, there are already projects on desalination, very much related, not 100%, but to this logic. Medina in Europe, that I've been coordinating for 5 years, was already considering membrane distillation and membrane crystallizers for the production of raw materials from brine. And the Megaton in Japan is already considering osmotic energy as a part of the story. And CRO in Korea, CRO 1, was very similar to Megaton, but today, 2014, I don't know if some of you were attending the first conference of this CRO 2 that was held here in Seoul, September 1st, last month. They are already spending here 70 millions for just realizing what I showed you in the slide before. Membrane distillation, membrane crystallizer for the recovery of valuable mineral from the brine of the desalination plant. So all these things are becoming faster than expected, real in terms of research. Not yet in terms of industrial development, because it takes time, but Korea made already an agreement with Saudi Arabia for working exactly on the problem of how to recover valuable components during desalination. Quite interesting, quite useful, and it will happen. You see here that these plants are already 1 million cubic meter per day. We saw before 3 plants, Algeria, Israel, etc., 500,000 installed in the third quarter of the 2013, just started. They are old because the new ones are double, increasing 100% the productivity of the system. So these things are moving quite faster. This is just Medina, as I was mentioning you, and Medina is just, as you can see here, all the pretreatment was to the reverse osmosis was membrane operation. At the end, we realized that the best membrane operation here is MBR. If you go in China, in Tianjin, they're already testing MBR as pretreatment to RO, and the post-treatment is the most important, was membrane distillation, membrane crystallizer. That's why this is becoming so important that we will rediscuss a little bit also during this part of this class, a little bit of this technology. And as you can also realize what we call a zero liquid discharge in this way, because basically you enter here with seawater or brackish water, and you go out with the salted water, but all the rest, there is no more brine disposal, because you can have, using membrane distillation, membrane crystallizer, you have just salts, crystals, coming out from the system. Fresh water on one side and solid material in form of advanced crystals. And you can see here Megaton, and you can find in the literature more reference, but if you look the technology that they were introducing, you see here osmotic power generation is already part of osmotic. So PRO was already in the logic of Megaton. Megaton now is close. Now they are making the industrialization of this, considering already not only production of fresh water, but already osmotic power generation. And when you go to, and all these plants is optimization of 1 million cubic meter class plus. They make a new class of plants, 100% bigger than the one installed that are starting to operate now, basically. Okay? And if you go now to Korea and you look to this sea arrow, you will see basically that the fallout is the same and the size of the plant was roughly the same. Here they are talking of huge single trucks. But if you multiply single truck of 36,000 cubic meter per day for 10, for 20, and they have, you can put 50, 60, you have 1 million, 2 million cubic meter fresh water per day. Huge plant, basically. What is more interesting that if you are looking to this sea arrow, the Korean story, in the second step, what is the one going now, they are introducing all the discussion I was mentioning before. Forward osmosis and RO, one different kind of pretreatment, using forward osmosis as pretreatment to reverse osmosis. That is one of the concepts. But what is more interesting that you can see down here, they are already considering new materials, a new pretreatment, new way to control the fouling, and the most interesting part for all of us that are working here, Korean is already introducing membrane distillation, membrane crystallizer for the recovery of valuable substance from the millions and millions of tons of brine that you are producing in desalination. And here is the real money. Forget about the water. What you can extract if you do in this way, what the cost of the water can be just production of the plant can be just $500,000, etc. But if you start to produce not water, but epsomite or thenardite, some of the salts that you can extract from the sea of high quality, you can pay back the investment in 6 months, not in 6 years, as was done before with just selling the water. So that's quite interesting, and this is $70 million of Korean money for the research. Starting September 1st was basically the first, I think, public presentation, and we also energy recovery again, R&D, reverse electrodialysis and PRO, and also capacity mixing, etc. So all the most advanced technology for energy production, for mineral production, and eventually also water. So they are completely focalizing the attention, as I was mentioning before, as a romantic vision. No more romantic. Koreans are not romantic. You are spending a lot of money for doing what is really necessary. That's quite interesting from my point of view. So again, this is basically the overall concept, and you can, the traditional, this is the system when you can have all the pre-treatment, the membranes, but this part here, the post-treatment, the brine disposal is no more a problem. Brine disposal will be the core of the process, and you will have membrane distillation and PRO also in this case, where you can produce energy. You increase the concentration of the brine. The brine from desalination is 1.5 roughly. No, seawater is 0.5. In traditional RO, where you can have a recovery factor of 50%, the brine is between 1.4, 1.5. Power density is still low if you are working with this concentration. If you combine MD and PRO, this 1.5 molarity can be 4, 5, 6. You approach precipitation. And in this case, you can arrive 20 watts per square meters. And with 20 watts per square meter, if really working for years, you can cancel nuclear energy, for example. Now, 20 watts, big number, and we are far away from 20, but people are already working 10, 12. We have a R&D working in Italy at the moment in REA Power project that is working about 10 or 12 watts per square meters. So it can be done, and shortly will be much, much more significant. Okay, keep in mind that you can have this logic that I showed also before, the forward osmosis and RO. That is also a way to increase the recovery factor, because you can clean and separate a lot of bivalences, a lot of salts, and minimizing the osmotic phenomena, and you can have a significant interesting reduction also at the end of energy production. So these things are moving, and this is another justification not only for attending the class, but for making research in this department in all these things. There is people here working on forward osmosis. There are people working on pressure retarded osmosis. There are people making membranes to be utilizing these kind of things. This is the money, Korean money, that I was mentioning before. You can see here a lot of the next, the budget that will go in the next year, quite significant, 32 billions of yuan, and in this case 26 billions. And what is interesting here, that is the way in which you're just designing a new system that create water, lead the future. And not for the water, because to create water means to create minerals and to create energy, not just the water. The water is already there. We don't create water. The water is eventually, we purify the water. But if you work on the water in this, with this kind of approach, basically you can produce energy, you can produce materials, solving the problem that really will affect our life, energy, depletion of raw material. That's a quite interesting approach. Maybe some of you will be involved in this kind of project, because this project is running here, basically, in Korea. Okay. Now let's see that for doing this, just to mention for the new students who don't know about, you have to develop, it's not so easy, you have to develop new membrane operation, which are very new for us recently, but less new when you see that now you are investing 70 millions in this kind of things, which when we were in class 3 years ago, we're not talking in this way because nothing was existing. Today, we have these things moving. But moving this new membrane operation means membrane distillation. And just to remember, some of you, we will try to tell something, that membrane distillation is a way to solve problems, as we are mentioning, but we need totally different kind of membranes. Membrane distillation has nothing to do with traditional reverse osmosis ultrafiltration. You have to develop a microporous hydrophobic system in which only vapor is going across, no liquid phase. And so you have to find new kind of materials, not traditional aromatic polyamide, etc., but strong hydrophobic materials that can be produced in hollow fiber configuration, flat sheet, but microporous hydrophobic. If you do this, you can solve the problem and well spend the 70 millions that I was showing before. And there is a lot of engineering. These systems are not very well designed as a reverse osmosis ultrafiltration. We still have to decide which one of the different configuration is the most interesting. And it will take some time for doing this. And we have to decide which kind of properties we will have at the end, and compared to the traditional, a lot of people are telling, we have distillation, why do we have membrane distillation? This has to be discussed and to convince the people that this is necessary if they are set PSI in the logic of process intensification, because conventional distillation has nothing to do with process intensification. Just the opposite, huge footprint, very, very large. Flexibility, zero. If you want to change the productivity of traditional MSF from 1 million cubic meter to 2 million, the only thing to do is to take the old plant and put in the garbage. If you want to do the same with membrane distillation, you just add few modules and you double the number of the modules, can be done in the same plant. So there is a high flexibility as requested, etc., etc. Membrane crystallization is something that will also follow, and we'll have exactly the same kind of properties. We can crystallize, not just concentrate, but we can crystallize our solute in appropriate final habits, to the point that we can produce the polymorph which is necessary. That means you don't produce, for example, magnesium, you're going to produce magnesium sulfate in the form of epsomite. You don't produce sodium sulfate, you produce sodium sulfate in the form of thenardite, etc., etc. For each one of these systems, if good researcher will make their job, will be possible to produce at a very high velocity, because this is the delta G of the heterogeneous compared to the homogeneous, And if you reduce activation, and all these processes are activated process, you reduce this activation energy going from for polyacrylonitrile to PTFE, you just basically increase significantly the kinetics, and you can produce very nice crystal, as you can see here, or very nice controlling the habits, the final habits, and all these data are already in the literature, and you can write to have a selective polymorph crystallization. Quite important in the biotech, in pharmacy. Here is glycine, gamma and alpha, but that can be done also in inorganic salts, I was mentioned before, epsomite, enardite, etc., etc. And we know how to do it. Now we have been slowly understanding and learning, and we will are publishing, if you are interested. We are just in the last few days, still today, by the way, sending to the editor a new book just on crystallization membrane assisted. It will be published in a couple of months, it will be on the shelf, because all these things are becoming quite important. You can redesign chemical industry or pharmaceutical industry trying to use more and more and to develop more and more at industrial level this kind of technology, and it's quite interesting. You can go from gamma to alpha, you can see how different they are, just changing the condition of the crystallization you can handle on the 10th floor on the term of axial flow rate, etc., etc. Interesting, a lot of fun. And here with paracetamol, etc. And if you remember the principle, for doing this, you have to understand what is going on. And now we start to understand. It's not easy, but what is happening, if you remember what I showed you before, we are controlling the activation energy of the heterogeneous crystal nucleation compared to the one homogeneous. And we are basically increasing activation energy, increasing the velocity of crystal growth, which means that crystals, the kinetic form of some of the crystals that normally were transformed in the thermodynamic one, these crystals are, if you produce very fast, you remove them from the equilibrium, so they will never be transformed in the past one. So this thermodynamic one will be totally different, and you can induce the formation of these other crystals, which were one time the kinetic one, the non-stable one. Quite interesting. If you can remove those, you will never form past one. And that's what is happening now. And that can be easily done. And as you know, you can do more than this, because now if you're a good engineer and you are just doing this warming up for making distillation with the same membrane, don't tell around, but it's exactly the same, instead of warming up, you can do other things. You can start to cool down. Instead of sending a warm, putting your thermostat on one side, try to put a cryostat and having a gas phase arriving, flue gases coming on the membrane surface. If they arrive at 95 degrees centigrade and you cool down a little bit to 80 degrees centigrade, 10 degrees, etc., you can condense everything that can be condensed, water and contaminants eventually, and so you have membrane condenser. And membrane condenser, if you go in the literature, are starting to become our paper, but now there are other people that are publishing, also in Journal Membrane Science, I think, membrane condenser, where you can control and extract the water, not from the sea, but also from the air. And there's a lot of water in the air. Or every time you have gases, there is a certain, they are asking from a cost analysis, only if you recover only 20% of the water present in the system is already paying back the investment. Also here, a lot of work has to be done. How to cool down? And that is engineering. You can cool down on one side, you can cool down on the other side, you can cool down by a stripping gas, you can cool down by having everything in a cryostat, etc., etc. Which one of this configuration is the best one is the role that young master student or PhD students are now doing, trying to design the best form, etc., etc., and so on. On the last issue of Journal Membrane Science, you will find membrane dryers, and that is one more. Membrane dryers means to compete with lyophilization. Lyophilization is a very, very interesting but complicated and costly unit operation. If you want to have a real power dry from of your pharmaceutical, of your catalyst, etc., you have to use a lyophilizer. Lyophilizer, big stuff with a lot of troubles. We are now trying to substitute normal, making the same process, lyophilization. Lyophilizer normally work at 80, 90 degrees centigrade to remove all the water to have powder. You can make the same operation with the same membranes, having a powder as fluidized bed, etc., using your membrane distillate microporous hydrophobic or also hydrophilic. And you can just extract the water in the vapor at 20, 25 degrees. So minimizing all the trouble related to the crust, to this cluster formation, etc., etc. And quite interesting also this one. Just to show with some flexibility, the same membrane, the same module, the same membrane some of you are producing on the 10th floor can be utilized in a dryer, in a condenser, in a crystallizers, in a distillation units, and more than this. At the end, the overall system, you can just have all these things in which you can use the crystallizer and the dryer, etc., in the same, just to solve all the problems that in principle you have. Just to remember, however, that is not so easy. If you want to do this, and you have to understand a lot of things that I was showing before, first you have to produce the membranes appropriate. And you already heard some story that is not easy. And some of you are involved in trying to optimize and making new membranes, not so obvious. But second, you have to keep control of other aspects. For example, pretreatment has to be innovative. You have to change the normal pretreatment. For example, if you want to produce the crystals, you have to avoid any contaminant organic in the seawater or in brackish water before reverse osmosis and before the membrane crystallizer. Otherwise, the benefit I was showing before will disappear. You can see here that the fluxes can go down with time, but more than this, the quality of your crystals can change. The organics also present in part per million, they can basically give you a much lower crystal growth rate, which means also it's more difficult to control the polymorph, because we learned that the crystal growth rate, I'll give you the possibility to have a specific polymer, can give a much higher CV. That means much higher distribution of the size of your particles. So the quality is going down, the cost is going down, and you can have smaller crystals if you cannot control, etc. So we need an appropriate pretreatment, and you have to change everything. Here are some data. We don't have now time to discuss about the data, but some is already in the literature. And if you want now to produce some of the things I was mentioning, it can be done. We are working with big industry today to produce already some of these things. We are working to produce this kind of, it's not here, but the kind of epsomite or thenardite I was mentioning. That means magnesium sulfate or sodium sulfate. One thing you have to do is to remove some species. Calcium always precipitate first. So if you want to crystallize magnesium or barium or strontium or other stuff, I have to remove the calcium. You have to find a way to block the calcium. In our case, what we do, we just separate in easy way by precipitation. 90% can be precipitate, and at the end you can produce recovery factor 93 and about 20 kilo of salts together with from 1 cubic meter of water together with this recovery factor. Quite interesting. Something similar can be done eventually with lithium. Lithium today, as you know, is strategic, becoming more and more a strategic mineral. Not easy, because lithium is very, very soluble and is very, very diluted. So if you want to extract lithium from seawater or from the brine of the desalination plant, still a lot of work has to be done, but can be done. And if you're looking at what we are doing, you can see that there is a lot of hypotheses, to the point that in perspective, we are today, I never went to a mining conference in my life, except recently, because you can go there and you can tell to the mining people that what they have been doing until now will disappear. In perspective, we are going to redesign mining. Mining tomorrow will be just from the big amount, millions and millions of tons of salts that we call brine, and that was a problem yesterday. Today I say, oh, we have to thank God that we have all these millions of tons of brine, because that will be the brine of tomorrow, the mining of tomorrow. How to extract a lot of minerals that are all in the sea, that we are discharging, combined with energy production and water production. Quite interesting if it works, and we will see how what can be done. And these are all systems that are just designed for doing this kind of operation. Some of you know already. For doing this, remember process intensification. Probably Professor Yamoli already mentioned that you have also to start to understand more what really you have in your hands. For example, everybody is working on PVDF. Now, some of you are aware that PVDF is not just PVDF. There are hundreds of different kinds of PVDF. PVDF exists in different kinds of polymorph, and each one has a different property. Some of them are polar, some are non-polar. Some of them are piezoelectric, some of them are non-piezoelectric. And when you form membranes and you want to really keep control of the final influence of this membrane, for example, in crystallization, we know that there is a lot of effect on the crystallization related to the surface property. Having a material piezoelectric or polar give you totally different influence on the crystal formation for a material non-polar and non-piezoelectric. So if in perspective, really we want to use, as Sierra 2 is predicting, this system to produce crystals, we have to know which kind of PVDF we are using, because that can induce, can change the condition for having the right appropriate kind of crystal we want to form, etc., etc. We will not have too much time to discuss about these things, but that's to give you a feeling of how the principle of process intensification are very fast penetrating in all these things that when I was making membranes years ago, I was talking about PVDF. I have no idea that PVDF was so complicated. But that is true for any kind of polymer, basically. And today, you must know about this, which was not the case until a few years ago. And there is a lot of difference. The problem of the solvents is another problem that everybody is becoming aware, because all the solvent we are using today for a system that has to be very effective in the industrial production has to be banned. All the polymer, all the solvent we are using in Europe for sure, with the REACH program, will be forbidden in 2, 3, 4, 5 years from now. So we have to study new solvents for making the membranes. And change the solvents, you have to start from scratch again. You have to start to redesign your phase diagram and to see the influence, the solubility in the solvents, the jellification point, etc., the crystallization, because everything will change. And that's the kind of work that, for example, is also in progress here. And the new polymers, ALAR, this is the case, more hydrophobic, not more hydrophilic. Forget about hydrophilic. There are so many hydrophilic polymers around. We have to look at hydrophobic in our case, because all this new technology will be based. And ALAR is becoming of interest not for competing with polysol, with hydrophilic material, but for competing with hydrophobic materials, and so on. And some of you are already aware, it's important to have this kind of morphology, to have very regular pore size, and that can be done. We are already publishing this kind of, the possibility to produce this kind of membrane, not easy, not roll to roll, but a small piece we are doing. And slowly, that will be done by phase inversion, but controlled phase inversion. If you go to the 10th floor, one of the machines is already equipped with a closed chamber, because that can be used eventually, we forgot talking yesterday, to have this kind of production, which is quite interesting. Keep in mind that we have been talking on the traditional water, energy, food, etc. It's much more than this. Membrane engineering has an impact on everything, and the other area, particularly interesting, for example, will be textile. Now, textile, you are already using a lot of membranes. People are aware of Gore-Tex. Gore-Tex is the most interesting case, but it will be much more than this. If you read this research agenda of Skyline debate, you will learn that in the future, medicine will be very different. Future means 10 years from now, 20 years from now, no more. There will be no doctor anymore coming at home and visiting you and asking. We will have a lot of signals continuously transferred to the hospital or to the doctors. They will have a record what is happening already today in the space. There is no doctor going to visit the astronaut when they are in the space. There is a lot of new textile with sensors that transfer, they analyze continuously your body, your blood, your water, etc., and they transfer the signals. And this is done using membranes, 100%. You can see these things already. There is a lot of textile industry will be very, very much redesigned, introducing a lot of new materials and new functionalities, antimicrobial materials and electronic textile and polybrominated materials for flame retardant control, etc., ventilation system, etc., because at the end, particularly using the same kind of polymers I was mentioning before, new polymers for hydrophobic microporous, perfluoropolymers in combination with other classes of compound, there will have a very high impact. So some of the material you are studying today for desalination, crystallization, etc., will have another utilization that is this one. And this is becoming huge. In this country, here in Korea, there is a single company already producing 5 million of square meters of one of these polymer flat sheet, just for making people happy when they go for during the weekend to make on the boat, etc. 5 million square meters of fluoropolymer, breathable, that can just make your light, but with good transpiration. Only in Korea, just 5 million. Korea and Bangladesh, really. But that can be done. And if you are smart, that will be a lot. These are all membranes. There will be membranes, which are, by the way, don't tell around, are the same membrane you are studying already, because the property at the end, if you understand, is very flexible system. You can utilize in any way. These membranes can control irritation, allergy, intolerance. You can have heat exchange, breathability. You can have, there can be waterproof, self-cleaning. You can immobilize the titanium dioxide, CO2, and you have, with the solar energy, they just destroy an effect of some oil, etc. Harmful chemical, physical agents, integrated sensor, this is the most interesting, for doing what is necessary, which, by the way, already exists. Because if you look to what the astronauts are using today, most part of these things that looks so future, not future at all. The only trouble, astronauts are 25 around the world today. And there are 25 of these, or this small number. Tomorrow there will be billions and billions of normal dressing based on exactly on the same material, in which today they have transfer of signals, selective control of some oxygen or CO2, etc., across, and a lot of the functionalities that we were mentioning before. The understanding and the correct design of most part of this is done by scientists called today membrane engineers. They are no more traditional textile technicians. They are membrane engineers who knows about transport phenomena in dense or porous film or fibers. Exactly what they are doing in some other case. But that will be one of the future. Not too many membrane engineers are involved in this because these are 25 men to be dressed. But when there will be 25 billions to be dressed, there will be a lot of membrane engineering involved in these kind of things. Okay, and that will be an example of the future that we will have. A lot of stuff, and just to close, keep in mind that when you are reading on the newspaper about tissue engineering and regenerative medicine, it's exactly the same story. I am a founding member of the World Society of Regenerative Medicine. And when they asked me, they wrote me a letter telling if I was going to be a founding member. I say, me, I have nothing, I don't know what is regenerative medicine. And they explained me why they were inviting, because they knew what I was not aware, that all the work on tissue growth and tissue engineering is related to membrane phenomena. When we are talking about membrane reactors, they know that membrane reactors is the way in which basically in the body already immobilized catalysts, biocatalysts are working to reproduce, etc. So when they founded the society, they were asking a couple of membrane engineers to be part of the staff because they knew that the information for them were our information. I had no idea what was regenerative medicine at that moment. I was very surprised, and now after I understood the situation. So today, today we are working at ITM on artificial kidney, artificial pancreas, artificial brain, which is most interesting, and there are people just who knows how membranes can reproduce artificial brain, for example, which is one of the most interesting areas today. If you go in the literature, you will find, because at the end, the membrane, you can use, this is an artificial liver. That is a system with, you have a combination, you see, you have these two normal module, these hollow fibers, where each one of these are different kind of membranes in this one and that one, because one membrane is doing one work and the other membrane is doing another work. And you integrate the functional, trying to reproduce all the functionalities of the real liver, but we, at least the two, we know how to do it, and that is a typical example for growing hepatocyte. The hepatocyte are the real microorgan that control the phenomena, but they are going here, and this is an artificial liver that is produced in a membrane institute, basically. And there is a lot of these things where these membranes are the function of acting as a scaffold. So the biomaterial scaffold, for instance, is a semi-permeable membranes with a well-defined micro and nanostructure capable of restoring, replacing, or enhancing tissue function as well to stimulate, etc., etc., etc. So we are still using all real cell, neural cell, hepatocyte, and lymphocyte, etc. But if you want to handle and you want to realize something, you have to do, that is the case of neural cell in the brain. If you want to realize this and to handle, membranes is the way of doing. If you don't want to use the real brain of your friends, which is not very polite, but you can reproduce an artificial brain, and on this artificial brain, done in this way with immobilizing this neural cell on the membrane system, you can use your new drugs, control the kinetic of some phenomena, etc., etc. Quite interesting, and that's another area that will go and go. Okay, that's just for telling why you are supposed to spend a few hours more in the next couple of months for understanding some of this process. We will discuss basically a little bit more on gas separation with membranes. We will discuss about energy production with fuel cell. We will discuss a little bit chemical reactors. So the topics that we have not been discussing in springtime, we will try to discuss here. Okay? Question, problem, comments? You will receive these slides that will be distributed before or after the class, so you can have the material. We will send you also some review paper or some other paper that can help you to read more about this topic from what I'm telling here. And if you need more clarification or information, room, what is 921, you can find me there. And any problem now? All clear for the moment. Okay, we meet on Friday. Thank you.